Okay, hello everyone. So we have a new topic. Our new topic is linear algebraic equations and how to solve them by using numerical methods. So what's a linear, what's a set of algebraic equations? So remember that while solving the Newton-Raphson, uh, we may have multiple equations, and in fact, sometimes these can be nonlinear in fashion. Certainly, we may have several unknowns to determine. For example, if you are solving a truss system by method of joints, simply you have several unknowns which are associated with each truss member, and then we have a number of equations which are equal to the number of joints. So we call such system algebraic equations, in fact. But in case of a linear, so these set of equations are associated in a linear fashion. As you see that x1 here is an unknown, x2 is an unknown, xn is an unknown, and then we have the coefficients a11, a12, a1n, and a21, a22, and a2n. And of course, these may be equal to some value, b1, b2, or bn. This set of equations are called linear algebraic equations. These equations are linear in the sense that the dependent variables, all the equations are linear by means of dependent variables. Dependent variables are x1, x2, and xn. Okay, so after making this definition, let's look how we can define such a system. Generally, we define such a system by means of matrices and vectors. Of course, let me remind you some of the fundamental things about the matrices. So what's a matrix? Matrix is a set of values. And certainly we have columns, okay, so which are vertical, and we have rows which are horizontal. So any matrix can have any dimensions. For example, here n by m matrix or n to m matrix here, okay? This basically means that we have n number of rows and m number of columns. How we define the member of a matrix? For example, I want to define the member of a matrix which is in the second row and third column. So this is my second row and this is my third column, and then I look at the indices. The first index shows me the row number. In this case, it is A2. And the second number shows the column number. It is 3 in this case. So this is the A23. Okay, it is the member of the matrix in the second row, third column. It goes like this. So you may have different, you may choose different members or elements of the matrix. What else? We may have row vectors. So what's a row vector? This is, for example, a row vector. As you see, so we have a vector with a number of elements or members m, and it is just made of a single row. You may have column vector. Then you have single column, and it has n, for example, in this case, n members. Certainly, the row vector is 1 to m matrix, and column vector is 1 to n. Sorry, yeah, this is 1 to m, and this is n to 1 column vector is an n-to-1 matrix. Okay, we may have different types of matrices. In fact, these are important points. For example, symmetric matrices. Now, this is our diagonal. Okay. If the values on either side of the diagonal are equal, then this matrix is symmetric. For example, let's look at this matrix here. It's a 3 by 3 matrix. So let's look at the element member of the matrix, which is in the first row, second column, it's 1. And in the second row, first column, it is 1 again. So again, third row, first column, it is 2. First row, third column, it is 2. So basically, if you draw a line along the diagonal, if the values on either side of this diagonal is equal, for example here, it's 1, it's 1, it's 2, it's 2, it's 7, it's 7, then this matrix is symmetric. What is the advantage of symmetric matrix? We are dealing with the computers. Now, let's look at this matrix. You have 9 elements, 9 members, 9 values here, and you have to keep all of these in the memory. But if you have a symmetric matrix, you only need to keep 6 of the numbers in the memory. This is such kind of, also it has some other advantages while solving such kind of such linear equations with symmetric matrices. Okay, how about the diagonal matrix? Generally, we represent the 0 members with empty. Okay, so let's look here. All the elements in this region are 0. So for example, A2, 3 is 0, A2, 4 is 0, A1, 2 is 0, A2, 1 is 0, A4, 1 is 0, and so on. All the members are 0, and only non-zero values are the values which are at the diagonal of the matrix. Such matrix is called diagonal matrix. Now, inversion of such a matrix is quite easy and simple. You just need to take the 1 over the value at the diagonal. So we will see it in detail. Okay. Okay, so this is one thing. Now, we may have other types of matrices. For example, sometimes we are faced with the upper triangular matrix. So what's an upper triangular matrix? So when you draw a line, again, along the diagonal, the values on the upper side, at the upper side of the diagonal are non-zero values. And below, they are 0. So such a matrix is called upper triangular matrix. So this is an upper triangular matrix. We may have lower triangular matrix as well. It is identical to the upper triangular matrix. The property is this. So all the values below the diagonal are non-zero, whereas the values on the upper side of the diagonal are 0 completely. We have an identity matrix. So identity matrix is the matrix which has ones at the diagonal. It's a diagonal matrix, but off diagonal values are all 0. And whatever you multiply with the identity matrix, you will get the same matrix as well. Okay, so this is what is called identity matrix. We sometimes have the banded matrices. For example, here we have the three diagonal matrix. As you see, we only have values at the diagonal which are non-zero, and there are two other lines. This is a three diagonal banded matrix. There are two other lines at which the values are non-zero. Rest of the values are all zero, as you see. In fact, this is a three diagonal banded matrix. You may have pentadiagonal, so which means that you have 5 lines of non-zero and septa 7 lines of non-zero values. What are the properties of matrices? So matrix operations are quite important for us because we will heavily use these operations in our computations. We generally use matrix algebra and matrix operations. For example, addition. Let's consider that we have two matrices, let's say A and B. Certainly the member at the eth row with the jth column will be summed with the corresponding member in the other matrix. So Aij is summed with the Bij, and it will form new matrix Cij. What it means, you can basically sum two matrices with equal dimensions. So the number of rows and number of columns must be equal in both matrices. And certainly the resultant matrix has the same dimensions with the matrices which are summed up. Subtraction, it is identical to the summation. Of course, this basically means that you only sum up the values in the corresponding places. So you sum up the value at the eth row, jth column, and subtract the value from this one in F, in matrix F, for example, in the eth row and jth column, and you form the resultant matrix. What are the properties? Of course, commutative. Summation and subtraction are commutative. So A plus B is equal to B plus A. Sorry, summation is commutative. Okay. It is also associative, which means that A plus B plus C is equal to A plus B plus C. So basically this means that first you make the operation in parentheses. So first you sum up A and B and you obtain a resultant matrix. Then you sum this matrix with the C. This is how you obtain. In this one, you first sum B with C and then you sum up these two matrices. Okay. Now, from time to time, we need to multiply a matrix with a scalar. In this case, we multiply all the members of the matrix with the scalar G. So this is our scalar quantity, and what we do is very simple. Certainly, our new matrix is the members of the new matrix is multiplication of the members of the original matrix with the scalar value. You multiply all the members simply. Okay, this is how we do the multiplication by a scalar. Now, next thing is multiplication of two matrices. In fact, this is critical, and we use it very heavily. In this case, what we do is, for example, let's say that matrix C is equal to A multiplied by B. Okay, we can show it like this. So this is the expression. The member of the C matrix C is nothing more than multiplication of the rows of first matrix with the corresponding column of the second matrix, and then you sum them up. You see, K is from 1 to n. It is AIK multiplied by BKJ. This basically means that you have an iteration over the rows, members of the row, of a row, which is the row I. And in fact, this will form the I component, and then you have the J here. And there is a summation over the K. So remember that K is from 1 to n. As a result, K is changing from 1 to n, and you multiply each value. In this case, here K is the row index. Therefore, while iterating on the row members in the first matrix, you are iterating on the members of the column in the second matrix. So this is how you do. This basically means that the sizes, the dimensions of the matrices has to be compatible, which means that the dimension of the number of the elements in a row in the first matrix has to be equal to the number of the elements in a column in the second matrix. Or in other words, here you can see it like this. A is a matrix and B is a matrix. Multiplication of these two, in order to multiply these two matrices, you see the number of columns has to be equal to the number of rows in the second matrix. Number of rows in the first matrix will form the number of rows, has to be equal to the number of rows in the resultant matrix, and number of columns in the second matrix will be equal to will determine the number of columns in the resultant matrix. So let's make an example. Now here we have X and Y matrices, and let's see how we can multiply it. For example, here we have a 3 by 2 matrix and 2 by 2 matrix. So this is a square matrix. Since the number of rows and number of columns are equal, if the number of rows and if the number of columns are equal, we call such a matrix as square matrix. So what we do is, first we move the second matrix upwards, then we will try to form the matrix Z. And let's see how we are going to do it. Okay, now first we take the first row, and then we take the first column. Now what we do is we multiply 3 by 5 and 1 by 7. So 3 multiplied by 5 will make 15, and 1 multiplied by 7 will make 7. Then we sum them up. Of course, the result will be 22. Now let's do the same thing. We take the second row and multiply it with the first column. So 8 multiplied by 5 is 40. 6 multiplied by 7 is 42, and the result is 82. So this will be the first member of the second row, and it will continue like this. For example, let's calculate the third one. 0, 4 and 5, 7. 0 multiplied by 5, let me clear this. 0 multiplied by 5 is 0. 4 multiplied by 7 is 28. And if we sum up them, the value is 28. Now, let's proceed further. Now, I will multiply 3 with 9 and 1 by 2. 3 multiplied by 9 is 27. 1 multiplied by 2 is 2. And sum up will give us 29, as you see. Now, we will continue with the second member of the second column. 8 multiplied by 9 is 72. 6 no, 71, yes. So 8 multiplied by 9 is 72. 6 multiplied by 2 is 12. And the result will be 84. Now, let's do the last operation. 0 multiplied by 9 is 0. 4 multiplied by 2 is 8. And as a result, we have 8 here. Okay, so these are the values that we have. This is how we do the matrix multiplication, simply. Now, what are the properties of the matrix multiplication? First of all, it is associative. So you can first do any two of the matrices. If you have 3 matrices, let's say A, B, and C, and for example, A multiplied B, you get a matrix, and then you multiply it with the C. Of course, I assume that the dimensions are compatible. This is equal to B multiplied by C, that is multiplied by A. Okay. It is distributive. So what's it? For example, you are summing up 2 matrices. let's say that B and C, then you multiply it with the A. Of course, you can distribute it. That's equal to A multiplied by B plus A multiplied by C. Identically, A sum up with B, if you add A to B, then you multiply it with C. Again, it is equal to A multiplied by C plus B multiplied by C. But unfortunately, the matrix multiplication is not commutative. So A multiplied B is not equal to B multiplied by A in general. This is one thing that you have to pay attention. This is in fact a critical issue. And even though the matrices are square, because the dimensions has to be compatible, remember that. So the number of columns in the first matrix has to be equal to number of rows in the second matrix. If you change the places, certainly the dimensions may not be compatible. Even if it is compatible, as is the case in a square matrix, then it may not be the case. So it doesn't have, matrix multiplication does not have a commutative property. Okay. Now, sometimes we need to calculate the inverse of a matrix, but how we define an inverse of a matrix? So consider a matrix, an arbitrary matrix, okay? Let's say that it's B. If you multiply a matrix with an arbitrary matrix, and if you obtain an identity matrix, that matrix is called inverse of the matrix. For example, here, for example, if you multiply A with B, and at the end, if you obtain the identity matrix, this basically means that matrix A is the inverse of matrix B, or matrix B is the inverse of matrix A. This is how we define the inverse of a matrix. Certainly, it is commutative. You can change the places. So A multiplied by A inverse, its inverse is equal to inverse of the matrix multiplied by the matrix A. As a result, you obtain the identity matrix. Now, we have an important operation. So how we define the transpose of a matrix? Remember that we always do the things or define the things with respect to the diagonal of the matrix. In fact, let's draw a line again on the diagonal. Even though the matrix here is square, it's not necessarily be a square matrix. I want to take the transpose of a matrix. So what is the transpose? So simply what I do in this case is I interchange the places in the rows and columns. And it goes like this. I change these members. So I change the places of this member with this one, this member with this one, this member with this one, and this one. So simply I turn the matrix with respect to the diagonal, and I obtain the transpose of a matrix. So look at the indices in this case. For example, the transpose of the matrix, the diagonal elements are keeping their places. That's okay. But look, it is A21. So remember that the first index shows me the row number, but here it is in the second column, because in the original matrix it is in the second row. So Again, with respect to our new matrix, let's say that this is equal to C. Sorry for this. Okay, let me clear it. So let's say that this is equal to C. So my new matrix C has the members switched, somehow mirrored. We can say that it's not mirrored, but their places are changed according to so you basically interchange the places of rows and column members in the transpose of a matrix. Okay, so this is what the transpose is. Finally, we have another operation that is the trace of a matrix. So what is the trace of a matrix? Trace of a matrix is nothing more than the summation of the diagonal elements, as you see. So this is called the trace of a matrix. You sum up the values at the diagonal. And this is called trace of a matrix. Last thing is the matrix augmentation. Sometimes we need to combine multiple matrices in different ways. You can add some more rows or you can add some more columns. This is called augmentation. We use it in order to find the inverse of a matrix, especially inverse of a large matrix by using Gauss elimination. So in this case, what you do is you append in another matrix. Either to the right-hand side, you can augment it in different ways, or you can augment to the left-hand side. You can add some more rows, and it's you can do lots of different things. In fact, now after all talking about all these things related with the matrices and how they are represented and their properties. Now, how can we represent a linear algebraic equations in a matrix form? So this is because this strongly simplifies our operations in computers. So what we do is we have the matrix. Generally, we have the coefficient matrix A. So we put all the coefficients in these matrices, and then we put a column vector here, and we say that it is X. Simply, A multiplied by X will give us the right-hand side of the equation. Then we write the right-hand side of the equation, the values at the right-hand side of the equations in a column vector as well. Now, we want to solve this set of equations. So let me go back to the first slide, then it will be much more clear. So let's look at this set of equations, which are on the right-hand side. You see, I can write this equation by a vector-vector multiplication. Remember that scalar multiplication of two vectors will give me a scalar value. In this case, it is B1. And I say that the first vector or vector of the coefficients are my first row. Now I go to the second equation. Then I extract the coefficients. Again, I write it as a vector scalar multiplication of two vectors. In this case, the coefficients vector will form my second row, and it goes like this until the last equation. Now, if I do it for all equations, let's go to my okay. Now basically I have a matrix of coefficients A, I have vector of unknowns, column vector, and I have vector of right hand side, again it's a column vector. The only thing that I need to do is multiplying, because I want to find the x, right? I want to find the values for the unknowns, values of the unknowns. Then what I do is I multiply both sides with the inverse of the A, matrix A. Now this multiplication will give me the identity matrix. Then on the right hand side, I have A minus 1 multiplied by B. This is a matrix vector multiplication. As a result, since I know that this multiplication will give me the identity matrix, as a result, so identity matrix is the matrix with the ones on the diagonal. So whatever you multiply with the identity matrix with, you obtain the same thing. If you multiply a vector with an identity matrix, you will obtain a vector. As a result, you obtain the values for the unknowns. So this is the column vector, this is the A minus 1 multiplied by B. Okay, so this is how we solve the linear algebraic equations by just calculating the inverse of a matrix. We will see the techniques that are used to calculate the inverse of large matrices.